Hello everyone. So we're looking at this example. We're looking to prove something interesting or something that might not be that obvious that we're looking to prove. So I've written it out what we want to look at. We're asked to prove that the equilibrium constant for the reaction of hydrochloric acid and ammonia is 1.8 times 10 to the power 9. Confirm this value. So it says, so we want to prove this. I can wipe that out now. But what we want to essentially prove is we want to show that if hydrochloric acid and ammonia reacts to form NH4 plus and water, the K value for this is 1.8 times 10 to the power 9. Now, the first thing that you will probably be like, what on earth did I do here? Is you might say, well, isn't hydrochloric acid HCl aqueous? And then doesn't this form NH4Cl, right? And yes, I mean, you can write it as such, but remember the net ionic equation for a strong acid, the moment that you put a strong acid in water, so something like HCl in water, then it forms H3O plus whatever the spectator ion is, or the anion is. And then the thing that actually protonates or reacts further is H3O plus. All right, so that's why we have H3O plus being the acid here. So remember, a strong acid is actually always written as H3O plus. So HCl is never the reactant, it's always H3O plus, right? So it's H3O plus NH3, giving us NH4 plus H2O. And I've written it as an equilibrium and not a product forming reaction, just because we're looking at a K value, and K values are associated with equilibrium. All right, so we want to prove that this is the case for that. So the way to do this now is let's look at each of these, or let's look at some equilibria to prove this. This question is not typically an exam question, it's actually just a bit of a thought-provoking question. So if we think about ammonia and its Kb value, when ammonia reacts with water, all right, to form ammonium, so NH4 plus aqueous plus hydroxide, it has a Kb of 1.8 times 10 to the minus 5. All right. And we can also make use of the Kw of water. So meaning that hydronium plus hydroxide gives us 2 water. And the K value for this expression is the inverse of Kw. Remember, Kw is defined as when water dissociates into H3O plus OH. So let's look at the sum of these two equations and what that gives us. So this gives us NH3 plus H3O plus aqueous plus OH minus aqueous plus H2O aqueous in equilibrium with NH4 plus aqueous plus OH minus aqueous plus 2 water liquid. And then comparing what's on the left hand side and the right hand side, we see there's an OH and an OH, and there's 1 water, and we can take off 1 water there. So that means we are left with NH3 plus H3O plus in equilibrium with NH4 plus aqueous plus 1 water. All right, and what did we do to get this? So how can we calculate the sort of K net for this? Well, summing two equations is like, what do you do with the K values? You multiply those K values. So now let's just call this Ka for interest, Kb times Ka. And that means we must take 1.8 times 10 to the negative 5 divided by Kw, which is 1.0 times 10 to the negative 14. And if you do this, then you get 1.8 times 10 to the power 9, which is exactly what we wanted to prove. So the point here was essentially to show you that you can determine the K value for acid-base reactions using Ka, Kb, and Kw for different reactions, just by manipulating and writing them, trying to sum them to get the reaction that you are after. So that's an interesting exercise for you to perhaps try and do, to determine whether or not a reaction is product forming. So that's why we would typically say, well, when hydrochloric acid reacts with something, right, so like NH3 aqueous, because that K value is so large, we would typically say this is a large product forming reaction, and that's why we don't typically write it as an equilibrium, because its K value is so large. It's a product forming equilibrium or product favoring equilibrium, and hence we write it as an arrow, right, because its K is so large. And you can determine that for yourself by looking at the K values for different reactions. So this is also a way to determine, this is technically what we calculated here, is the Ka for HCl. It's very large. All right. So, that's actually just for the acid-base, sorry, it's for the acid-base reaction of HCl and ammonia. All right. Very interesting. I hope this, like I said, I don't think this is not a typical exam question. It's more for interest, more for just a bit of thinking and reviewing a couple of concepts. But I think you can, perhaps for those of you who appreciate this, I hope you enjoy that. All right, I'll see you in the next video, and thank you for watching.